Alright, we're in chapter 14 talking about solutions, and we've talked kind of abstractly about the concentrations of solutions. We've used three different terms: saturated, unsaturated, and supersaturated. However, chemists like to know quantitatively, not qualitatively, what type of solutions or what the concentrations of solutions that they have are. Meaning they want to know numerically how much solute is dissolved in that solution or in that solvent. So it turns out that chemists have concentration or quantitative expressions that they can use, different calculations to predict or to calculate how much solute is in a solution. So there's different types of concentration expressions we can use. So we're going to go through the equations first, and then we're going to practice using them in problems and setting problems up and knowing which one to use when, given with the given information we're given in the problem and what we're asked to find. So the first type of concentration a chemist can talk about is the mass percent. And remember, the percent of anything is always the part over the whole. So if you're looking at mass percent, you're looking at the mass of the part over the mass of the whole. The mass percent of a solute in a solution is the mass of the solute, so the grams of the solute, divided by the mass or grams of solution times 100%. There's also a mass percent that's called parts per million. And it's basically the mass of the solutes divided by the mass of the solution, but instead of percent or per hundred, you multiply that times a factor of 1,000,000. And this is used when you have a very, very sparse amount of a solute in solution, so hardly any. So instead of a percent-wise, you might have a very small decimal form. You would multiply times 1,000,000 so you could get the concentration on workable terms, like a whole number. Alright, so mass percent is grams of solute over grams of solution times 100%. Now, let's remind ourselves of what a solution is. A solution has two parts. If I say the mass of the solution, what if I'm given a problem and it gives me the mass of the solute and then the mass of the solvent? Well, the mass of the solute will go in the numerator. If I'm not given the mass of solution, though, remember that the grams of solution, because there's two parts to a solution, is always the grams of the solute plus the grams of the solvent. Okay, so just keep that in mind. A solution is the solute plus the solvent. So if you're not given the grams of the solution, just add those two together. Alright, what's another concentration term we can use instead of mass percent? We can also use mass volume percent. This is very convenient if you have solids dissolved in liquids. Usually you will measure the mass of the solutes, the solid, out on a balance. Then you'll dissolve it into a certain volume of liquid, milliliters, and easily you can come up with a mass volume percent. So a mass volume percent is the same type of equation. It's always part over whole for percent. It's the grams of the solute over milliliters of the solution. Once again, solution is solute plus solvent. And then times 100%, 100. Times 100. I don't know why I put the percent in there. I get like that sometimes. Alright, what is a volume percent? Let's say that you have two liquids. It's very convenient for a chemist to measure the volume of a liquid in a graduated cylinder or some other type of pipette, volume tool, or instrument, versus going and weighing the mass of a liquid. So when you have liquids dissolved in other liquids, a lot of times chemists will use a volume percent. This is just the volume of the solute divided by the volume of the solution times 100. Usually volume is going to be in milliliters. So you have milliliters of solute, milliliters over milliliters of solution. You always need to make sure that your volumes are in the same unit. They don't have to be milliliters. They could be liters over liters, centiliters over centiliters, but just make sure they match so that they can cancel out, because you're going to end up getting just a percent in the end. If they don't have the same units, like one's in liters and one's in milliliters, you're going to have to convert them to the same. You should be pretty good at that by now. All right, let's look at molarity. Molarity is a little bit different. I'm going to put an asterisk by molarity because in terms of chemistry, there's 2% that chemists use most. They use the mass percent and they use molarity. Molarity is different. It's not a percent as a concentration expression. Notice it has the word mole in it, and molarity kind of looks like liters. Molarity is a concentration term, and it has 2 units. So the unit molarity is a big M. So that's the unit for molarity. But the other unit that's derived from the molarity unit is moles per liter. So the unit molarity can be substituted for moles per liter. Both of those are the same units. They mean the same things. And it's because of the way molarity is measured. Molarity is calculated as the moles of the the moles of solute divided by liters of solution. So it's moles of the solute divided by liters of solution. So that's where we get our molarity term. So if you ever see something that says 2.5 molar aqueous solution, it's 2.5, take the molar out, and it literally means 2.5 moles of your solute in 1 liter of solution. That's what molarity means, moles per 1 liter of solution. All right, and the last we have is a little bit different, and this concentration term is going to be used a little bit later in our colligative properties. But molality. Molality is a small cursive type M. So molarity is a big M. Molality is a small m. Molality is the moles of solute divided by kilograms of solvent. Why am I writing this and underlining it twice and putting an exclamation mark on it? If you notice in all of the equations above, it's always solute over solution. And what are the 2 parts of solution? Solvent plus solute, right? Alright, so it's always the part over the whole. When we get down to molality, it's solute, technically the moles, because we have molality, the moles of the solute, divided by kilograms of solvent. So it's the part over the other part, so not part over whole. Molality is little different, and usually chemists only use the molality when doing calculations with something called colligative properties, melting point and boiling point changes of solutions, and osmotic pressure type things. So we'll use that one a little bit later. But these are the equations that we're going to use to calculate concentration. Now, as usual, I give you the equation. That's one thing. It doesn't usually help. It just helps you not have to memorize. But you need to know how to use the equation on your own. You need to know which equation to use from problem to problem. The best way to do that is to go ahead and practice as many problems as possible where you use these equations. So let's go ahead and practice some problems. Okay, let's look at the first problem here. It says calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of sodium chloride in 150 grams of water. Okay, remember, with word problems, there's usually lots of names of compounds. They're asking you to do things. There's different units. There's numbers. There's all these things in the word problem. Are you going to understand exactly what to do just by reading the problem? Sometimes. Some people are really good, but I have to go. And when I read a word problem, I'm telling you this so you don't get discouraged. I find most of the time when a student reads a problem, they go, I don't know what to do. And if they don't know what to do, there's 2 things that they end up doing. The students that tend to succeed will reread the problem slowly, and they will figure out what they're given. they'll figure out what equations they have to work with, and they'll try to work between those parameters. I find the students that are generally unsuccessful are the ones that just read it and say, "Ugh, I don't understand what I just read," and they just stop. Don't be that student. No one understands what they read entirely the first time they read these problems. So always go back and read them slowly and start looking at what you're given and what you're asked to find. And I only tell you that because I can understand it can be discouraging. So don't feel like you're behind because you have to read the problem again. Everybody has to read the problem again. Alright, so let's read it again. We're supposed to calculate. Now that's important in its own, that word calculate, because that means we're probably going to use an equation, right? Alright, so we're going to calculate the percent mass. So because we're asked to calculate percent mass, you're going to go grab that equation. We just looked at the equations. The percent mass, also known as the mass percent, that equation is the mass of the solute, or the grams of the solutes, divided by the mass of the solution, or the grams of the solution. And that's how I abbreviate solution, by the way, or all chemists do, because we have to write it so much, times 100%. Alright, so I've got my equation. Once you know what you have to calculate, go grab that equation first. So check, we've got the equation. So we want to calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of sodium chloride into 150 grams of water. Okay, why am I reading that part slowly? We have two compounds given. We have sodium chloride and water. We need to distinguish which one is the solute and which one is the solvent in order to place them correctly into our equation. Remember that a solute is always the agent being dissolved. So it says you're preparing a solution by dissolving 50 grams of sodium chloride into the water. Remember, the solvent is doing the dissolving. The solute is being dissolved. So the sodium chloride is being dissolved here. This is our solute. The water is the solvent. It's doing the dissolving. When you have these concentration equations, it's going to help you out, these word problems, to always label the solute and solvent. You don't want to get them backwards because you'll get the incorrect answer. Alright, so now that we know we have the solute, let's go ahead and start. I'm just going to ignore this for now. Let's go ahead and start solving the problem. The percent mass, or I guess I won't write it that way. There's several ways to write percent mass, but the percent mass is going to be equal to grams of solute. We said there's 50 grams of sodium chloride, and now we need the grams of solution. Remember, the solution is the solute plus the solvent. So I'm going to have 50 grams of my solute plus 150 grams of my solvent, okay, times 100. This is the part of this is a simple problem we're starting with that most people will miss. They'll put 50 grams of sodium chloride over 150 grams of water. That's the solute over the solvent. We want the solute divided by the entire solution. So then we just do our math. It's 50 grams divided by 200 grams times 100. So this is a quarter, or 25%. So the answer here will be 25% mass. 25% sodium chloride in the water, right? All right. So that was a pretty simple one. Let's go on to the next one. It says calculate the mass of sodium carbonate and water needed to make 350 grams of a 12.3% solution. Alrighty. Okay, let's go back and see what we're doing. It says calculate the mass of sodium carbonate and water needed to make 350 grams of a 12.3% solution. So what are we asked to calculate here? We're asked to calculate the grams of sodium carbonate and the grams of water. So we're asked to calculate two different things. We're probably going to do this stepwise. Whenever you're asked to calculate more than one thing, you always calculate one thing first, and then you'll usually draw from that information to calculate the other. So calculate the mass of sodium carbonate in the mass of water needed to make 350 grams of a 12.3% solution. Now notice that we're given a mass here. What is this mass? This is the mass of take the number out, a mass of a solution. This is the mass of the solution. This is the grams of the solution. What is this then? This is the mass percent of the solution, 12.3. Why is it important that I label all these things? Well, if we're going to do a calculation, usually we need, like I said once again, we need the equation. So we need to know which of these concentration equations to use. Here, now we know that we're given the mass percent, so we need the mass percent equation. The percent mass is going to be equal to the grams of the solute divided by the grams of solution times 100%, times 100. Now, why did I leave the solute blank? What's the solute here? Calculate the mass of sodium carbonate in water needed to make a solution. Usually, whenever you have an ionic compound, we said it's soluble or insoluble in water. Water is typically the solvent. So solids, sodium carbonate is a solid. It's an ionic compound. They always are solids most of the time. So the water is the liquid. It is the solvent. This is our ionic solid. It's our solid. It's our solute. And the water is our solvent. Okay, so I'm going to write that I need the grams of sodium carbonate because for the mass percent equation, it's always mass of the solute over mass of the solution. So the percent mass of sodium carbonate is the grams of sodium carbonate over the grams of solution. Let's substitute in what we know. We know the percent of the solution is 12.3%. We know that the grams of the solution in the denominator is 350 grams. That's the entire solution. Do we know the grams of sodium carbonate? No, we're asked to find that. I'm going to put an X here. This is my unknown. I don't know the grams of sodium carbonate. So that's the first thing I'm going to solve for. Now I'm going to get the percent out first. So I'm going to divide this side by 100. Plain old algebra here. Divide this side by 100. That will get the percent out of this equation. So you divide by 100 here. I'll have 0.123 equals X divided by 350 grams. Alright. Now I'm going to multiply, just some simple algebra here, by 350 grams, multiply times 350 grams to isolate X. So I've got my grams on top and bottom there. I multiply 0.123 times 350. I'm going to get X. X equals, what's 350 times 0.123? X will equal 43.1 grams. Okay, so my grams of sodium carbonate, my solute, that's what X was, is 43.1 grams. This is my sodium carbonate. So what is the grams of my water in order to make this solution? Well, remember the grams of the solution equals the grams of the solute plus the grams of the solvent. Okay, so if I don't know what the grams of my solvent is, it's grams of solution minus grams of the solute. And our solvent is the water. So here we have 350 grams given for the solution. we subtract 43.1 grams for the solvent, and keeping significant figures in mind because we're going to round to the one place, I'm going to get 306.9 or 307 grams of water. Okay, so we have 307 grams of water and roughly 43.1 grams of sodium carbonate. If we mix those together, dissolve them, we'll make the 12.3% solution. Alright, let's look at the next problem here. It says normal saline is a 0.9 mass to volume percent sodium chloride solution. What mass of sodium chloride is needed to make 50 milliliters of normal saline? Okay, let's read that again. Actually, I checked this once because I was pregnant, I was dehydrated at the hospital, and I looked at my bag of saline there, and it was actually 0.9 mass to volume percent sodium chloride. So this is a real-world problem. Somebody might say, hey, I gave someone at the hospital some normal saline solution. If I gave them 50 milliliters of that bag, how much sodium chloride did I just give that patient? And that should be a question that you end up being able to answer relatively quickly. If you know the equation, you can figure it out. So let's figure it out here. First of all, what are we given? You see that we're given a mass volume percent. The percent mass volume equation is always the mass of the solute, so grams of the solute, over, the volume, would be the milliliters of the solution times 100%, or times 100. Alright, so in a normal saline solution, what is the solute and what is the solvent? We see here that we have sodium chloride. Whenever you're given the percent and you have the agent down there, like percent sodium chloride, whenever that's written, that's always the solute that's given. So when it says percent magnesium hydroxide, percent sodium carbonate, percent sodium chloride, that is the solute. So the mass volume percent here that we're given is 0.9. 0.90, and that is the grams of sodium chloride divided by the milliliters of solution. Alright, it says what mass of sodium chloride. So we want to know how many grams of sodium chloride will be in a certain volume, 50 milliliters of normal saline. Alright. By the way, what is the solvent? If it's not given, most of the time we can assume with an ionic compound that it's water. So that's just a general assumption a chemist makes. Alright, so here's our unknown. Sometimes I like to circle my unknown so I know where it is. Alright, we've got 0.9 equals x over 50 times 100. I'm going to simplify that so I can actually see what I've written. So we've got 0.90% equals x, the grams of sodium chloride, over what was the milliliters of solution, 50 milliliters times 100. Okay, now I'm going to do some simple algebra here. I want to isolate x. So the first thing I have to do is I have to get rid of the 100 here. So I'm going to divide both sides by 100 to get the percent out. So when I do that, I get I'm going to get 0.0090 equals, because I'm dividing 0.90 divided by 100, so I'll move the decimal places I messed up, didn't I? Nope, 2 places to the left, I didn't mess up. 1, 2. Alright. 0.0090 equals x divided by 50 milliliters. Okay. Let's see here. X divided by 50. I'm going to multiply both sides times 50 now. Algebraically, I'm going to isolate x times 50. So 50 times 0.009. I think you should get gosh, I'm having a hard time tonight, 0.45 grams. So you will need, if you delivered 50 milliliters of normal saline to a patient, inside of that 50 milliliters was dissolved 0.45 grams of sodium chloride. All right? So once again, it's just, most of these problems are just figuring out what equation is being used, what concentration expression you're being given, pull that equation, substitute in what's known or what's given, and find what's not given. And if there's additional steps, you can figure out along the way. There's always, you need to identify the solutes, the solvent, and the solution, and the concentration term in each one of these problems. All right, let's look at the next one. It says, what volume of a 6% by volume ethyl alcohol / water solution. So we have a solution of ethyl alcohol and water. Okay? One of these is our solvent, one of them is the solvent. We're given the percent, 6% by volume. So this is our percent volume. So milliliter over milliliter. What volume of the solution, so how many milliliters of solution contains 200 milliliters of ethyl alcohol solute? So the ethyl alcohol is the solute. The water is the solvent. If we know we have 200 milliliters of the solute, the volume percent is always the milliliters of our solute over the milliliters of our solution. We're not given the milliliters of solution because we're asked to find what volume of a solution contains 200 milliliters of ethyl alcohol. So this time we're asked to calculate the volume of the solution that will contain 200 milliliters of that solute. All right, so actually this problem, we're going to grab, like I said, the volume percent again, just like we did that was mass volume previously. Now, they all look the same to me. Okay, here's the thing that you need to notice about this one. Our unknown that we need to solve for, our milliliters of solvent, is in the denominator. A lot of students set this up correctly. They'll get to this part. However, they'll get the wrong answer because they'll miss the algebra. We want to isolate x. The first thing we're going to do is we're going to divide both sides by 100, right? To get rid of the percent. So go stepwise with your algebra. So we're going to divide that by 100. We're going to get 0.060 milliliters to milliliters equals 200 milliliters divided by x. So x is our unknown. Do you see how our unknown's in the denominator? When you isolate x in algebra, don't you always have to bring it to the numerator? Yes. So what we're going to do is we're going to multiply both sides by x. And we do that, we get the x out of the denominator and we bring it to the numerator. So when I multiply both sides of x, I have 200 equals 0.060 x. Now I divide both sides by 0.060. Those will cancel. I've got 200 divided by 0.060. X is going to equal, what is it going to equal here? I get on my calculator 3,333.33333333 milliliters. All right? Remember, we're going to go with significant figures here to two significant figures. So 3333.33 repeating, two significant figures is going to be 3,000, not 333, but 3,300 milliliters. All right. So what does that mean? Okay. Let's say that you have a 6% solution of ethyl alcohol in water. If you wanted to get 200 milliliters of the ethyl alcohol solute into a vessel in the solution form, you would have to pour out 3,300 milliliters of the solution, and it would contain 200 milliliters of that ethyl alcohol. Alright? That's what that means. Let's look at the next one. Alright, the next one is a molarity problem. In molarity, you're going to have to practice a lot of these. I'm just going to show one of each because for these videos, I don't want them to be too long. So I'm showing a couple practice problems of each. Practice as many problems in your book as possible because you could see different versions of the same equation being used, different word problems, and you might be asked to solve for one variable versus another. This problem says calculate the molarity. Now molarity is a big M. Molarity is moles of solutes divided by liters of solution. So it says calculate the molarity of a solution prepared by dissolving 9.35 grams of potassium chloride, and then I'm given, then I'm given something beside that. It says 74.55 grams per mole. Do you remember when you have two units and one of them is a mole? You usually have a conversion factor. Mass per mole is molar mass. This is the molar mass of potassium chloride. I might need that if it's given. So it says calculate the molarity of the solution prepared by dissolving 9.35 grams of potassium chloride in enough water to make 250 milliliters of solution. Okay. Let's make a list of everything we've got here. We've got 9.35 grams of potassium chloride. We've got 250 milliliters of solution. Okay. When we need to calculate molarity, we need moles of our solute. Our solute here is KCl. It's potassium chloride because that's the ionic compound dissolved in water. So we need moles of potassium chloride in liters of solution. We're not given moles of potassium chloride, we're given grams of potassium chloride. So the first thing we have to do is we have to convert this to moles. Now there's two ways you can do this. You can use the standard conversions, where you use units to solve problems. So grams of potassium chloride, we can convert from grams to moles using molar mass. The molar mass is 74.55 grams per 1 mole. So I've got a grams on top. I'm going to put the 74.55 grams of potassium chloride on bottom, and I'm going to put the mole on top. 9.35 divided by 74.55, equals 0.125 moles of potassium chloride. So really quickly I can convert grams to moles. So I can put that in here now. Molarity, which is what I need to calculate, that's my unknown, is 0.125 moles of potassium chloride divided by the liters of the solution. Okay. Now, by the way, there's another way I can get moles real quick. Mass divided by molar mass equals moles. And that's exactly what we did. We took the mass, we divided by the molar mass, and we got moles. So if you still cannot do conversions, and you're going to need to learn them, but in order to get the mole, you're going to have to convert grams to moles a lot in this chapter. Okay, a lot of the times, if you need a mole, you're going to be given the mass instead. Mass divided by molar mass equals moles. Alright, so you could have just done it that way instead. That was what I meant by the second way you could do it. Alright, it will give you the same answer. It's just an equation versus conversion. Mass divided by molar mass equals moles. Alright, now we need the liters of solution. Notice we're given milliliters. Whenever you're given milliliters, you just divide by 1,000 to get liters. So what 250 milliliters is 0.250 liters. Now why did I divide by 1,000? Well, This goes back to the conversions. And hopefully now you remember all your metric conversions because they're so important in this class and in chemistry or in science in general. But remember that for every 1 liter, you have 1,000 milliliters. So I've got a milliliters on top and milliliters on bottom. So when I converted, I said 250 divided by 1,000. So when you go from milliliters to liters, you always divide by 1,000. That's what I meant by that. And divide by 1,000 means to move the decimal place 3 to the left. 1, 2, 3. So you end up getting 0.250 liters. Always watch out with molarity to make sure you have liters of your solution. Alright, so now we can calculate the molarity. We converted to moles and we converted to liters. So 0.125 divided by 0.250, that's half. So with significant figures, that's 3 significant figures, we have 0.500 molar solution. There's 2 different ways you can write mole. So when we have molarity, we say it's a so many molar solution. That's how we read that. 0.500, and usually the molar is written beside it, but I ran out of room. I'm bad. So the M goes there. It's just hard to see it's an M. You can either write M for molar, or you could literally write moles per liter, because molarity means moles over liters. So you could write a big M, or you could write the moles per liter. No, both. Alright? So those are some examples of calculating concentration using the equations. Practice every problem you can until you understand it completely inside out. You know which equation to use. You can do any conversions to get to where you need, and you calculate correctly using proper algebra. Okay? Alright.